Hello everyone, in this video I'll be talking to you about deep learning and let's get started. We have a lot of things to cover. So to start with, I'll start with the motivation behind deep learning. So basically what scientists did was they thought of replicating the human brain. We as humans think and do our actions with our brain, and this brain is the most important part. That's the reason for our intelligence. And when the scientists tried to explore how this brain functions, they found something called as a neuron. There is something called as neuron, and this neuron is basically a small cell which looks like this. This is the head of the neuron, and here we have the tail of the neuron, right? And there will be a stem like this in between. And in medical terms, this is basically called as a synapse or a dendrite. I'm not sure about the names, but this should be dendrite, and the stem over here is basically called as axon or something like that. So these are the neurons that's responsible for our intelligence. Basically, if we see something, we are able to identify the image or the vision or the speech or the hearing, whatever we do, right? All these things are possible because of these neurons. So what happens is that if you see something with your eyes or with your nose, if you smell something, or if you taste something with your tongue, or if you touch something hot or cold, your skin is there. So there are different types of sense organs. These are sense organs, and we can just think these are just inputs. These are inputs. We can also take ears here. So these are just inputs that we receive from this world, and these inputs are sent into these neurons. So we have a neuron here, for example. So this is one neuron, and the inputs are sent into this neuron, and this neuron passes the information that it received to another neuron. So there will be billions and billions of neurons within our brain, and these neurons are responsible for providing the way of how we perceive this world. So this passes some information to the another neuron, and this phenomenon just passes until we reach the end goal of what the world we perceive. All of these things happen within milliseconds. For example, if you're watching this video and listening to the audio that I speak, you can comprehend and interpret what I'm saying and what you're seeing. All these things are made possible because of the information that these neurons share with each other. Then finally we get the output. So as I said, these information processing takes within seconds, and these are the important things that's responsible for our intelligence, and these neurons are responsible for whatever we learn something new, something like that. So what the scientists thought was, why don't we create some artificial neurons? So these are natural neurons that's occurring in our brain. So the question is that why don't we create some artificial neurons and make computers intelligent, like how we humans think and how we humans make decisions whenever we see something or hear something or something like that. So that was the whole idea behind the history of creating artificial neurons. So what happens is that here we have inputs like this. So similarly, instead of eyes, if we can feed computers with images and videos, so we can do that. Images, videos could be an input, or we can send audio as an input, or we can send text data as an input, and we can also send tabular data as an input. There can be a lot of data. For example, if I want to predict a given image is a man or a woman, or whether a given image is a cat or a dog or something like that. So what happens is that these data here would be sent into some artificial neurons. I'm just drawing circles here. So these artificial neurons try to learn like how these human neurons process some information from the world that we perceive and sends to the next neuron. Similarly, the artificial neurons that the scientists create will also process some information, and it sends to another neuron and another neuron, and finally we get the output. Right. This is the motivation behind how scientists thought of deep neural nets. We'll dive deep into what's a neuron and what it does, how is it able to capture all these informations and all of the other things. But before that, I would like to add some more information to this. Whenever we were small, when we were kids, we used to see a lot of new things. For example, if we just see a cat, if you just see a small cat with this pointy ears and some sharp eyes, and it has a tail, and it has a very flexible body, and it's so calm and makes some noises, something like that, and it has some mustaches like this. For example, these are what I described just now are just the features of a cat. So these are the different features with which we could identify that this is a cat. Similarly, we tried to see a few cats in our life, and we understood what a cat is by based on their features. Similarly, these neural nets will try to understand the features of whatever we are trying to train upon. For example, if you are similarly, we saw the cat example, right? Similarly, if you are trying to send a lot of images to the neural network, the images of cats and dogs, then the neural net would understand, okay, cat is something that has a pointy ears and there has a longer tail and smaller in size, whereas a dog is bigger in size and it doesn't have pointy ears, rather it has flappy ears and looks cuter than a cat, something like that. So these are different examples of how neural nets try to understand the features from the inputs. So that's the whole idea behind how these neural nets try to learn new information. They basically try to understand the feature. So if I want to give a very easier example rather than this cats and dogs, I'll draw something like a mango here. So let's assume this is a mango and this is an unripe mango, right? This is not ripened, so that's why I use this green color. And then we have a ripe mango. Okay, so this is just an example so that you understand what I'm trying to say. So this is a ripe mango and we have an unripe mango. Now we need to create a machine learning model so that given a couple of features from these mangoes, it has to predict whether the mango is ripe or not, right? So instead of giving ripe and unripe, I will have 0 for this. 0 meaning it's unripe and 1 meaning it's ripe. Got it? So now let's take two features as example. So one feature is nothing but the weight, and the other feature is the color of the mango, or the color of the fruit, basically. So here we have weight. So the idea is that whenever the weight increases, obviously the the color also so whenever the weight increases, there's a good chance that this mango could be ripe, right? So for example, let's have an example like the weight of the mango is say 50 grams and the color is and the color is 0.7 or something like that. Here let's assume 0 is very close to green and 1 is very close to yellow. So if it is 0.7, it's somewhat near to yellow, and if it is 0, it's very close to green, right? So let's take another example. Let's say 55, and then I have 0.4 maybe. It's somewhat greenish in color. And let's take another example. I have 100 here, and it's 0.9. And then we have a different fruit. We have a different mango fruit with weight 90, and here it's 0.95, and so on. So this is what we call a data set, and these two are the different features of this mango. So we can usually the features are represented with X. Let me take this as X1. X1 is the feature 1, and then we have X2, which is color or which is the feature 2. Right, we have two features, And in our data set, we have one more column called as the target or the label. Right, I'll write target or label, or sometimes this is also called as an output. Now we need to predict whether this first mango is ripe or not. So we have the data set, and this data set has the ground truth, which means along with these input features, we'll also have this data. And usually the targets or the labels are indicated with the letter Y. Right. So here this is 0, this is 0, this is 1, this is 1. Okay. Now what we can do is we can try to plot this so that let's see if we can understand something out of it. So first what I'll do is I'll just first of all I'll just plot these weights in one axis and then have these targets here. So let's take this one, weights here. We have the weights, and that's the only axis that we have, and we have the X and the Y. Right, we have the weight and the label. So I have 50 here, so let's assume 50 lies somewhere over here. This is 50 and 55 is closer to 50. I'll mark it here, and let me mark this with green because the target is basically 0, which indicates that this is an unripe fruit. So I'm just drawing with green, and I have 100, so we have 100 over here, and there is 90, so 90 lies somewhere here, so I'm marking this with yellow. So from this we could sense that there is some gap between here, which is a good indicator of okay, this is a separate thing and this is a separate thing. But if you also take the color into account along the y-axis, let's see what happens. So I'll have weight over here on the x-axis, and we'll have color on the y-axis. And now let's try to plot this. And the color over here ranges from 0 to 1, where 0 is where 0 indicates green color and 1 indicates the yellow color. And if there is something 0.5 here, it's a mango that has both the colors equally. It's about to ripe and it's not so unripe, right? So that's the thing here. So I'll plot the points here. So we have 50 with 0.7, so somewhere over here, 50 and 0.7, and then 55 and 0.4, somewhere over here, and then we have 100 and 0.9. I'll take a different color for this, probably red color. 100 and 0.9, so we have 100 over here, and we have 0.9 over here, and we have 90 and 0.95. So we have something like this. So if we have some data points like this, so these are the different data points that we got from our data set. So this is basically called as a data set. So this is a data set. And after we understood our data set, we got some points like this. Now, is it possible for the machine to predict the differences between the ripe mango and the raw mango given this data points? And the answer is yes. So basically what we can do is we can just draw a line somewhere like this, or draw a line like this. It's not mandatory that the line should be only like this. It can also be a straight line or whatever. So let's just assume that this is a line that we could draw. Then in that case, we can easily say, okay, whatever the points that's on the right to this line are ripe mangoes, and the points that are left to the line are unripe mangoes, right? For example, if I get a new point, say if the weight is 150 and the color is 0.9, which lies somewhere here. So now I can predict, okay, this point here lies to the right of this line. So this should be a ripe mango, something like that. So how are we going to predict this line? So that is the essence of machine learning and deep learning. So given the data points, that is we have the inputs, that is the features, that is x1 and x2, and also the target, that is y. Given these both in our data set, we can just predict this line and just classify the two different categories in the points. So this is the whole idea, and this is what something that we are going to focus throughout this course. And let's now directly jump in. Alright, let us now assume that we have some three input features here. I'll name them as x1, x2 and x3, and we have a target variable y. Okay, and there are many values within this x1, x2 and x3. Let's take some example values, like the x1 is 1.5, and then we have x2 as 0.2, and x3 is minus 3.1. And the y value is 0 or 1. So y would take values like 0 or 1, and given these features we need to predict what y is. Okay, so and let's assume this is the first record, and let's take the second record, that is the second row, and let's have some another random set of values here. So I'll have minus 0.1 and 3.33, and then I'll have minus 1.76, and the value of y is 1. Okay, so let us just assume that we have some I values like this. So like 1, 2, we'll be having I values. In mathematics, we represent this data set mathematically as something like this. So here you can see all these numbers over here are called as real numbers, and in mathematics real number is basically denoted by the letter R with an additional vertical line over here, and this is the representation of a real number. And here how many dimensions do we how many records do we have? We have I records, right? This is I, so we have I records. So here x of I, that is x1, x2, how many records in I are there? So xi belongs to real number, because all of these data are real numbers. And what's the dimension of x? That is how many x features are there? There are 3 x features, right? So we write 3 over here. So this means there are I records of x with 3 dimensions of real numbers. So this is the usual indication in mathematics that we follow. And then similarly we have it for y. So in y there are also I records in y, and all of these belong to a real number that has zeros and ones, right? But in this case there are only 2 possible values that y can take. So instead of writing it like this, we have a simpler way of writing this, since it has only 2 values, whereas x can take a range of values, so we cannot write them within a specific set, but for y we can definitely write it in a specific set. So instead of writing it like this, what we can do is we can write yi belongs to a set of 0, 1. So this is our data set. So in mathematically we'll write like this. So xi belongs to features of inputs of shape 3, and yi belongs to a set of 0, 1. And let's assume if we have some d dimension, instead of 3 dimensions we have d dimensions, then we usually write xi belongs to a real number of shape d, right? So this is the notations that we will follow throughout this course. And with that said, now let's start architecting our first input neuron and the first neural network. Okay, so we'll take the same example dataset over here where we have 3 inputs, and the output label y could take 0 or 1. Okay, so now I'll draw 3 nodes here. So this is for x1, and this is for x2, and this is for x3. Okay, so x1, x2 and x3 are the values over here. And now what I'm going to do is I'm going to pass these inputs into something called as a neuron. This is a neuron, just assume this is a neuron, and this neuron takes all these inputs and does some processing and gives some output, and that output is then passed into another neuron. So this is in another neuron, and this neuron also does some processing, some information, and provides us an output. Okay, now we'll give layers. So this is the first layer, and this is indicated with the letter 0 or the notation 0, and this is the 0th layer, and this is basically called as nodes or inputs or input neurons or something like that. Okay, and this is the first layer, and usually this is called as a hidden layer, and this one has only one neuron. In real world it can have many neurons, like the first layer can have 100 neurons or 1000 neurons or even 1 million neurons, but for learning purpose I initially start this with one neuron, and as we go on we'll understand how many neurons to keep and what's the ideal neuron size and all those things. So for time being, just understand or just come along with me with this one neuron, and we'll see what this one neuron does. And then here we have the second layer, which is the output layer, and this one also has only one neuron, right? Here the number of neurons or the nodes in the 0th layer is 3, and we have one neuron in the first hidden layer, and we have one neuron in the second layer. Okay, so now let us just focus on this one neuron and see what's happening inside this neuron. So we have x1, x2 and x3, and all these values are passed into this neuron, right? So we have the x1 value as 1.5, and then x2 value as 0.2, and x3 value as 0.3, right? We'll just, for time being, we'll just take this one, this first row, and see what's happening over here. Okay, so we know that the value of x1 is 1.5, and the value of x2 is 0.2, and the value of x3 is minus 3.1. okay, so these three inputs are now fed into this neuron, and every neuron is responsible for two things. One is called as the pre-activation, so this one is responsible for something called as pre-activation, and the one above it is responsible for, so just understand here there's something called as a pre-activation. It has a prefix pre, right? So if there's a pre-activation, there should be something called as a activation or a post-activation, right? So after that, after the pre-activation, the neuron does something called as an activation, right? So there are two things that a neuron does. So one is pre-activation, and then the other one is activation. Now let's see what's a pre-activation and what activation is. But here we have three inputs, and these three inputs are going into this neuron. And whenever these three neurons are going into three inputs are going into this neuron, it doesn't just go just like that. It is going to be multiplied with some random values that we call as weights. So let me write W1 here, and I'll write W2 here, and I'll write W3 here, right? So these are some random values. Just imagine these are some random values, and let's give some random numbers over here. So I'll give 0.1 for this, and I'll give 1 for this, and I'll give 0 for this, right? So these are just random values that I'm initiating here. So basically, even in neural networks, the weights are initialized randomly. They are just random values out of nowhere. But as we go through the course, I'll tell you what are the good weight initialization techniques and all those things. But for time being, just imagine these are some random values that we are saying over here. So here I'll just erase this thing out so that we get some space. Cool. Okay. All right. So here we have x1. Here we have x1, and that x1 will now be multiplied with this 0.1, and we have this x2, and this x2 will be multiplied with w2, and we have x3 which will be multiplied with w3. And let's see what the calculation look like. So I told that x1 will be multiplied with w1, x1 will be multiplied with w1, and then x2 will be multiplied with w2, x2 is multiplied with w2, and then we have x3 that's multiplied with w3. So x3 is multiplied with w3, and after we multiply all these inputs with the weights, what we are going to do is we are going to sum them all like this. And there is one other factor that we are going to consider, which is called as a bias. So we have something called as a bias here, and I'll represent this as b1. and this bias is going to get added with this pre-activation, right? So I'll denote pre-activation with the letter A. I'll write A1 here. A1 is equal to, and then this bias doesn't have any inputs associated with it, so it is just going to be get added over here. So this is the first calculation that a neuron does. So it takes the inputs, it assigns some random weights, it multiplies the inputs with the weights, and it sums up all those inputs and weights and adds a small positive value called as bias, right? And this A here is something called as a pre-activation. This is called as a pre-activation. Now after we get some value over here for A, then there is something called as an activation that happens. I'll tell you what an activation is. So there are a lot of functions that's available in the world of deep learning. There is something called as a sigmoid function, there is something called as a softmax function, there is something called as a ReLU function. So there are different types of functions. For time being, let's just fit onto one activation function called as the sigmoid activation function. Sigmoid is nothing but 1 by 1 plus e to the power of minus x, right? Here instead of x, we will be substituting the value that we get for A1. Okay. So why do we use this activation function? What's the importance of it? So basically, if I don't use any activation here, the values are going to get evolved and it's gonna get summed up, and it would end up in a bigger positive value or a random value overall. But these activation functions tend to shrink these values into a certain scale, and also gives non-linearity into our network. Let's assume what's non-linearity is a good question. So here just assume that we have some data set like this where this is a feature, right? And we have some points over here like this. Now is it possible to split or classify these points with a straight line? This would give us bad results, this would also give us bad results. Anywhere when you put a straight line, it's not going to give us good results. It's not classifying the green points here with this purple points. So what a good model does is it tries to draw a circle around here, so that any point that comes here can be classified as the purple point, and any point that comes inside the circle can be identified as a green point. Okay, so whenever we have complex patterns in our data set, it's not possible for us to linearly achieve that. Linear here represents a line. So in this case, we need a circle which can basically differentiate between the purple and the green points. So in order to bring this non-linearity into our neural network, we always need something called as an activation function. These activation functions can destroy that linearity and bring in some non-linearity into our architecture. So that's why we use activation functions. There are a lot of activation functions that I'll discuss later, but at this point in time, just stick on to this one function called a sigmoid activation function. I'll also dive deep into what sigmoid is, when to use it, how to use it, and all those things. Let's assume that we have H1. I'll probably use a different color. Maybe I'll use purple. So I'll denote the activation as H1, and this activation is nothing but I'm passing a softmax activation function on A1. So this is nothing but H1 is equal to 1 by 1 plus e to the power of minus A1. This e is nothing but an exponential, and let's now substitute and see the values of A. So A x1 is 1.5, and it will get multiplied with 0.1, and it will give 0.15. So this term over here is 0.15, and plus we have 0.2 here, so this will be 0.2, and plus we have minus 3.1 multiplied with 0 is 0, and plus we have a bias term over here, right? We have a bias term over here, and let's assume the bias is 1, just a random value again. So this is going to be 1. So the A1 value is nothing but, here we have 0.15 plus 0.2, which is 0.35, and then we have 1.35, right? And this is going to be 1.35. So we calculated the A1 value to be as A1 value to be as 1.35. This is A1, and this is H1. So we need to pass softmax of, to calculate H1 we need to pass 1.35, and this is going to be 1 by 1 plus e to the power of minus 1.35. I'm not going to calculate this now, I'm just putting a rough estimate of what the value would be. I'm putting this as 0.6 for example. This may be a wrong value, but just stick on that this is some right value. Now this neuron has done both of its jobs. It has calculated the pre-activation, and it has also calculated the activation, and it has given out some value, and that value H1, so H1 is equal to 0.6. so that's the output of this neuron, right? And now what is going to happen is, the input that this neuron sent out is going to be the output that this neuron gave is going to be the input of the next neuron. Okay, so let us just go here, and let's give a new weight here as W4. This is again going to be a random value, and the value of H1 is nothing but 0.6 that we have here, and that is going to be multiplied with another weight called 0.4, and that is also going to have a new bias. This is B2, and let's take B2 value as 0.1. Again this is a random value. Let's take the value of W4 as 1 for example, and now here we would have 0.6, that is the input of input that's coming into this neuron, and this neuron is also responsible for two things. The pre-activation A2, here we already used A1, so I'm using A2 here, and the second one is the activation, that is H2, right? Now let us calculate A2. So A2 here will be equal to H1 into W4 plus this B2, right? So we know that H1 is 0.6 and W4 is 1, so 1 multiplied with 0.6 is going to be 0.6, and we have B2 as 0.1. So here A2 is nothing but 0.7, and this 0.7 is now applied on a activation function H2. So let's take the same activation function, that is sigmoid. So H2 here will be equal to sigmoid of 0.7, right? So now let's take the H2 value as 0.4. Let's just assume that the sigmoid of 0.7, instead of x we substitute 0.7 here, and we get the value of H2 as 0.4. And we have now reached the end of our neural network, right? And this is the output neuron, the final neuron that we have, and this is going to output H2, which is our estimate. This we call as y hat. So here we have the actual y. The y here is the actual value. The actual value is 0 in the ground truth is 0, but here the estimate, the hat over here is called as an estimator, and this y hat in itself is an estimate. So we are just trying to provide an estimate of what the actual value could be. So here we provide y hat value as 0.4, but we know that the ground truth value here is 0. So we know that the ground truth is nothing but 0, right? So the ground truth is 0, and here we have the predicted value as 0.4. Now we need to come up with some number to indicate how good or bad the prediction is. So here the output and the estimate doesn't deviate so much. It's quite close to each other, that 0 is quite close to 0.4. So maybe we can take a squared lossy error function, for example, which may give us y hat minus y the whole squared. So this is a way to just get a number, to indicate how good our prediction is. So in this case, I would get 0.4 minus 0 the whole squared. That would give me 0.16. So this number indicates how good my prediction is. Suppose instead of 0.4, if I got 0.9, right? If I got 0.9, which is very far away from 0, right? 0.9 is far away from 0, and my loss here, this is basically called as a loss. This is a number to indicate how well my prediction is, how good or bad my prediction is. So this is 0.9 minus 0 the whole squared, that would be 0.81. So you can see 0.81 is a huge number, whereas 0.16 is a smaller number. So this indicates that when my prediction is close to 0, I'm getting a smaller number, and when my prediction is far away from 0, I'm getting a bigger number. Right. So this is basically the loss function. We can have different types of loss function. For example, here I have the squared error. We can also have logarithmic functions. We can have different types of loss function that will explore throughout this course. But for time being, just imagine or just understand that loss is something that is used to indicate how good or bad your prediction is. Now, this entire thing that we calculated right now, right from the inputs to the weights multiplication, the pre-activation and the post-activation, and then following it up with different neurons, and finally calculating the y hat, which is an estimate, and calculating the loss function from that estimate and the ground truth, is basically called as forward propagation. This is called as forward propagation. So this is what we have seen till now, and now there are a lot of interesting things that we are yet to explore. Now we'll dive deep into how these neural networks work whenever we have complex architectures. Like, for example, what if we have 20 neurons in the hidden layer, and what if we have 5 hidden layers, and all those things, right? We'll dive deep into all those things. And if you have any questions till now, take a break and just go to the comment section and post your questions or comments or concerns.